Hi everybody, we're going to work on drawing a trigonometric problem with directions. So to start with, we would have a normal compass bearing, so north, south, east, west, with west on the left hand side. Sometimes we're going to change the orientation a little bit to help us draw in 3 dimensions. And where a direction doesn't lie exactly on north, south, east, west, we need to use a bearing to say how far away from north, south, east, west it is. And there are 2 ways to do this. The first is with a true bearing. A true bearing is always measured from north clockwise. So start with the north line. If we have 0, 3, 0 true, that's the bearing value. It's always 3 digits. And the true, or the 3 digit, in some cases the t's aren't put there, indicates to us that we go clockwise from north. So 30 degrees clockwise from north is that way. We are going to be heading in that direction. 270 degrees true, start at north, go around 270 degrees, we're going to be going in this direction. So start by drawing a small north line, measure the angle from north clockwise, draw the ray. Compass bearings, similar, but this time we're going to start from north or south first and then go east or west. So north 25 degrees west, we're going to go north, we're going to start from north and then go west. So here's north, go west. How far west? How many degrees west? 25 degrees. So with south 45 degree east, we'd go south first. We're going to head in the easterly direction, 45 degrees. There we are. That's the direction we're traveling. So start with north or south, check if going east or west, and then measure the angle, draw the ray. A couple of examples, one from O.T. Lee, one from Sadler. So Don sails his yacht 5 kilometers from P to Q. Here's P, here's Q, here's R. From Q he sails his yacht to R, from here to here, and that's 8 kilometers from P. Here's P, here's R, 8 kilometers. The bearings of P and R from Q, so we're going from Q to P and from Q to R. So from Q to P and from Q to R, yeah. So the first one, Q to P, is south 30 degrees west. From Q, south 30 degrees west. P is down there. And Q to R is south 45 degrees east, south 45 degrees east in that direction. And we have to find the distance between Q and R. So that's this length here. So to do that, we would look at this and would say, well, we need this angle here, and if we have this angle here, and we can find that length there, and we would need the sides on either side of it, which we have, but hang on, we'd have 2 unknowns in our cosine problem. That'd be the normal way we'd set it up. But there is another way to set it up, which I'll show you in a sec. And then there's the more traditional, well, let's work with what we know. We have a side and an angle opposite it. We have another side here. We could work out this angle. Once we'd worked out that angle, we could work out the third angle, and then we could use cosine rule to solve x if that's what we wanted to do. One way is quick, one way takes a long time. Let's start with the traditional route. So we're going to find R. So if we find R, we can find P. If we find P, we can find x. So sine problem, these 2 and these 2. Set up here, we find R, it's 37.14, that's the angle in there. Then we can find P by subtracting the other 2 internal angles, and we get 67.86 here. Then, to find X, we would use this angle that we've found. We have this side, we're given these 2, so it makes sense to use the Q's, and we'd find out at 7.7 kilometers. But it's a fair amount of working, and if you look in your calculator, you'd be doing all of that. There is a one-line method of getting to 7.67 or 7.7, which is just to say, well, I've got this angle and this side, which is the requirements for the cosine rule, and I've got this side and I want to find that angle, and so I put that over here as I would because I know it. Normally this would be the unknown, but we know it this time. We know the angle, we stick that over here. We know 5, we'd put that here and here, And this unknown here, we're going to put there and there. Now, if we had to solve this algebraically, it would be a pain. But because we have a CAS calculator, we can just jam it in, tell it to solve it, and it will give us the answers. It gives us one negative solution. We can ignore that. We're not interested in negative distances. And there's our 767 there. So difference in working, all of this or this. And this is often overlooked, so it's a good thing to know about. Now, the second thing it wants us to do is to find the bearing of P from R. Now, when we did this the long way, we happened to find R. If we'd done it this way, we would have had to have discovered R using sine or cosine rule. Once we know this angle here, and we already knew that angle there from our parallel line knowledge, that north-south line is parallel to that north-south line. If that's 45 degrees, that must also be 45 degrees. That means that this angle here is 360 take 45 take 37.14 will give us the true bearing of P from R, which is 278 degrees, which, if we convert that to a compass bearing, 278 is 8 degrees over, subtract that from 90, gives you north 82.1 degrees west. So from north to that line would be that measurement there. Could we have got that easier? Yeah, we could have just added those two together, couldn't we? That would have given it to us too. Okay, so first problem solved. So what we should have just done was found R and then added it to 45 and then constructed the compass bearing. That would have been quicker. Sadler 1C, that's a different problem. This is one of those three-dimensional problems that are hard to see unless you can visualize it. Well, that's a fairly obvious statement in hindsight. So the question says, points A, B, and C lay on flat ground. So here's A, B, and C. From A, the bearings of A, B, and C are 330 degrees and 18 degrees respectively, and we have a vertical tower. So here's the vertical tower here, and here's a really small diagram. So I drew that and thought, well, that's stupid, that's no good. So I drew it a little bit bigger. Here's my north line here, 18 degrees to C, 330 degrees to B. Here's the tower. Now, if I hadn't tilted north a little bit, the north line and the tower would have sat on the same line. It would have been hard to understand which meant height and which meant north. So similar to what we do in isometric, I've just tilted it to the side a little bit. And now I can say north is this way and height is this way. But this diagram was still too small, so I drew it bigger again. There's my 18 degrees. There's my 30 degrees from north. Here's my 40 tower. And we had to put in the angles from C to the top of the tower and from B to the top of the tower were 20 and 12 respectively. So there's the angles of elevation from the two positions B and C to the top of the tower. And we have to find the distance BC. So to do that, I broke out the two triangles from the three-dimensional shape. So ACT is over here, 40 is the height of the tower, 12 is the angle of elevation, AC is 188.19. I did the same for the second triangle, TAB, and height, the length AB was 109.90 meters. See if my pen's working. Oops. Then I can find out BC because I know AB and AC and the angle CAB. This angle in here is obviously 48. It's there. There are the lengths we were talking about earlier. So BC squared is 19.815. 19815.46. Take the square root of that and you get 141 meters for here. Now, something I thought would be good to know is that once you've put this line of working in your calculator, to take the square root, just take the answer and raise it to the power of 0.5. From index laws, you'd know why that is. It's easier than putting brackets around all of this and trying to do it all in one line. Sometimes splitting things over two lines makes things a lot easier to see, and if you're checking for errors, it's easier to see over multiple lines than it is over the one. So I hope that helps. And if you have any questions, let me know. Thanks, everybody.